going to get rid of. I was wondering if you had a preference for blackboard, chalkboard writing versus me using my iPad to write. I mean, you're not seeing me use my iPad to teach, but I was wondering if we change over to the iPad mode of teaching, if that's going to affect you. Maybe we can try out one class and so on. Okay, it's good. Getting a little harder to write on the chalkboard. I had a couple of injuries on my fingers. So if my writing is a little bad today, forgive me for that. Okay. All right. Any questions or clarifications before we proceed with class today? Homework is due on Sunday, but if you need an extension of a day or so, let me know. I'm more than happy to do that. I have office hours on Friday as well. I'm going to be changing my morning office hours on Friday to an afternoon time. So I'm meeting from 10 to 11, but I want to do that from 1 to 2. And then I will go from 4 to 6. Okay? All right. And I'll send an email with the Zoom meeting ID and so on. All right. So let's continue with our problem, which is going to probably take up the majority of our day today. Let me not use a line here. Alright, so I'm going to redraw the figure. You don't need to, you already have it. And then we will look at the kinematics of the problem, and then we'll start setting up the kinetics. Okay? X, Y, Z. Okay. And then we have a cone that is spinning. Apex is at the origin. And we said that we will set up a frame that is attached to the body of the cone, and we call this as E1, E2, and E3. So this is vector E1, and this is IJK. K hat, so this is E1, E2, if I use my iPad, I would have just brought out the previous lecture's figure. It would have saved us some time, but I think this is also worth it. Then we have the particle, which is attached by means of a spring to the center of the apex of the cone. This is the particle P. We call this as frame F1. This is frame F2, omega of F1 slash F2 is known to us. F2 slash F1, capital omega, K hat, capital omega need not be a constant, it can be varying with time as well, so I could have an omega dot, which is the angular acceleration of the cone itself. Stiffness K for the spring, linear spring. Stiffness K. I'm going to call the undeformed length of the spring as L0. Okay, so the deflection of the spring is the difference between the deformed or the stretched length and the unstretched length of the spring. Okay. Then we set up another coordinate frame relative to the frame F2, and this is the one that we have. So I drop a perpendicular onto the E1, E2 plane. From there, I have the position vector R, point B. Distance here was a value R. Angle is measured with respect to the E1 frame, call that as phi. And we had a set of unit vectors which were ER here, then E phi, which is perpendicular to ER and on the same plane as ER. This is point B. This is E phi, and then the cross product of ER and E phi gave me EZ, which was in this direction here. Now, one thing to mention here, and this is E3, I'm sorry. one thing to mention here is that I am labeling this also as E3 because this direction does not change. This vector is always going to be aligned in this direction even as the particle is going and traveling inside the surface of the cone. Otherwise, I would have to call it as a different name. If it was, for example, not a particle, but if it was a sphere with a finite dimension, then I would have to call it by a different name because that vector need not be the same at all points in time. Okay, so they will change. And we call this angle as alpha here. This was the cone angle. I constructed a plane. As you can see here, and then we wrote the position vector and so on. So RO slash P slash O. And before that, omega of F3 slash F2. This was phi dot in the E3 direction. Okay, the direction of increasing angle phi. And if I use the right hand rule, if I curl my fingers, my thumb is going to be pointed along the E3 direction. So that's going to be my omega of F3 slash F2. And then if I add these two up, I get F3 slash F4. Okay, so omega F3 omega plus omega. Either E3 or in the K direction. E3 is the same as the K direction. Alright, position vector from last time. So RER plus some Z E3. Z was the distance from the point P to point P. So this is Z. This is R. And we related Z and R by making use of the right angle triangle there. So we said that Z is R by tan alpha. Alpha is a constant. Okay, it's a cone angle. And so we were able to write RP slash rho is RER R by tan alpha E3. We differentiated this. I'm not going to do the differentiation for this. We obtain the velocity as the following. So it's by dp with respect to the inertial frame. Okay, this is the velocity. P slash O with respect to the inertial observer. So from now on, one thing I want to point out, if I'm writing the kinematic quantities, if I'm writing it with respect to the inertial frame, I'm not going to keep carrying along this tag of the inertial frame. Okay, it's kind of understood that we're writing it with respect to the inertial frame. Vp slash O, if I write it out, it's R dot ER, then R dot tan alpha E3, and then R times phi dot plus omega E plus. Okay, so this is the full thing, and then differentiation of this will give me the acceleration. So to get the acceleration, why do we need the acceleration? Because we're using Newton's laws. So I need to do force balance. Force is mass times acceleration. So I first write the acceleration, then we go into the kinetics of the problem where we start looking at the forces and so on. And we'll see how it happens. Acceleration. This is the rate of change of that entire thing with respect to F1, which I'm going to split into two pieces. This is d by dt with respect to F3. You can write it with respect to F2 as well, but with respect to F3, and then omega F3 plus F1 cross. I want to write it with respect to F3 because the particle is defined using the F3 coordinate. Okay, related to E1, E2, and E2. all you have to do is perform the differentiation. When I perform the differentiation of the first term, I am going to be differentiating only the quantities r dot, the quantity r dot tan alpha, and all of these guys, because they are being differentiated with respect to the particle frame unit vectors. So they will not undergo any time derivatives. So if you look at the first term, this is just r double dot er. Then I'm going to have r double dot by tan alpha E3. And then I'm going to have r dot times phi dot plus omega E phi. That's one. That is keeping phi dot and omega fixed, I differentiate r. Then keeping r fixed, I differentiate the sum of phi dot and omega plus r times phi double dot omega dot E phi. This is the first term. Okay? So that is this guy. I still need to do the cross product. I'm going to write out my triad somewhere here. R E phi so take the omega vector plus phi dot plus omega E3 crossed with the velocity vector, that entire big thing there. So that's going to be r dot er, r dot, r dot by tensile fraction, r dot by tan alpha. That's going to be E3 and r times phi dot omega. That's this. Okay. And what I want to do next is I want to collect all these terms that are in the same directions. Okay, in the E phi direction, in the ER direction, in the E3 direction. So let's do that. This cross product here, if you look at it, E3 cross with E3 is not going to make any appearance in my problem, in my solution, so I can just take off that particular term, okay, because it's cross product of the same vector as itself. E3 cross ER is going to give me something in the E phi direction, so this is in the E phi direction, the cross product. E3 cross E phi, look at the triad. I'm going against the grain, so that's minus ER. So if I take that, and then this guy, that's minus. I'm going to get rid of all of this here. Then I write my acceleration vector. I'm going to split it into three things. Components in the ER direction first. So that's going to be one fellow here. R double dot ER. And then I have R times phi dot plus omega square in the negative ER. So that's R double dot. Minus R times phi dot plus omega square, which should make sense, right? There is a radial component of the acceleration in the R direction, this is the centripetal component of the acceleration in the r direction, pulling it in the negative ER direction, which is typically what you'd have seen if this was a two-dimensional flow. Then collect all the E phi terms. So I've done this guy. So E phi, I have one here, one there, two of them. And then I'm going to have one more coming from here. So that's r dot times phi dot plus omega, which is going to be the same as that, and that's your Coriolis component of acceleration. If you see a factor of 2 in acceleration, that's Coriolis. Okay, so once again, there is an r dot phi dot plus omega term in the E phi direction. Cross product of E3 and ER gives me something in the E phi, r dot phi dot plus omega, added up with that. Am I making sense to everybody? Okay. Skipping some steps here. So plus 2 r dot phi dot plus omega. This is your Coriolis. And then I have r times phi double dot plus omega dot E phi. That's your tangential component of acceleration. R times phi double dot plus omega dot. And then the last one in the E3 direction, there's my guess there's only one term there left. And that is this guy here. R double dot. And alpha. Leave this here and also write the velocity up here. We need that. Slash O is r dot ER, r dot phi and alpha E3, r times phi dot omega E phi. Any questions, please? Once again, as you can see, we are not using any canned formulae. For the most part, we are just using that angular velocity addition, which is just common sense, and we've derived it. And based upon that, we derive the acceleration, we do the kinematic analysis for all of these things. Good news in the Lagrangian setup is you just need to stop only the velocity. You don't need to do the acceleration analysis there. Okay, because the differentiation of the Lagrangian terms will give you the accelerations as needed. So all of this dirty work is not needed. There are other types of difficulties, of course, but it's much better than this stuff. So I'm going to call this big term here as AR. Okay, so I'll write it down here if everybody can see, people in the back. I'm writing down something here, okay? Just saying that acceleration of P slash O is AR, ER, A phi, E phi, A3, P. Where each of these terms corresponding to the unit vectors dr, E phi, and E3, they are your acceleration components. Okay? All right. Now we come to the force analysis of the force balance. We are saying that this is a rough cone. Okay, so I need to redraw my figure again for the force balance. So bear with me. Okay, so here is IJK. Particle. ER. E3. forces. So I'm drawing the free body diagram of the particle. What do you think will be the forces acting on the particle? Yes.
The gravity.
Gravity, right? Always gravity. So there's one force which is G. That's one force. Yes.
Spring and normal force of the cone.
Spring and normal forces. So the spring force will always be directed radially along the length of the spring. Okay. So in my case, the spring force will be pointing this way. So this is Fs. So Fs is the spring force. I'm just going to write it as Fs. Is K times delta, which we need to calculate. We haven't done that yet. That's the spring force. That's along the line joining the particle and the spring. Normal force is between the particle and the inner surface of the tube or the cone, which means it is going to be pointed in the normal direction. Be careful, this is not the same as EF. You'll see that in a minute. Okay? This is not the same as the direction ER, it is at an angle to the direction ER. Okay? Any other forces, and we are assuming friction is present. So obviously there has to be friction. There will be two components of the friction force. One component is as the particle is trying to slide along the slant length of the cone, there is going to be a component of friction force. Okay, so I'm just going to assume that it is directed this way. So this I'm going to call as F, and I'm going to call it as some subscript T, and you're going to see why. Then I'm going to have another component of friction force, because the particle is also, if it were not moving along the slant length, it would be spinning along with the inner surface of the cone. So there's going to be a friction force in the E phi direction. Does this make sense to you? Okay. So that's going to be in the E phi direction. I'm going to call it F phi. Okay. And so I need another figure to describe the directionalities of these things. I'm going to do here. But before that, I'm going to write down the formula. So the net force on the particle, and no, well, I'll draw the directionalities in that. Cone. Okay. I'm going to assume that the direction, or I'm going to call the unit vector along the slant length of the cone as E suffix t. So the particle here. There is a unit vector E suffix t. Then if I'm drawing the unit vector E phi, that's going to be in this direction. These two are perpendicular to each other. Okay, they are the two directions for the friction force. The direction along the slant length, and then the direction along the surface of the cone in the E phi. If I take the cross product of these two, I'm going to be getting the normal direction. And I can define however I want to take the cross product. So I'm going to say the cross product of ET cross the E phi, if I use the right hand rule, this is going to be the normal direction, which is pointed this way. So ET cross E phi gives me En. Does this make sense to everybody? The direction of the friction forces are orthogonal to each other. There is one friction force along the slant length of the cone, and there is another friction force if you imagine the particle spinning without sliding along the length of the cone. There is another friction force in the E phi direction. The third force that completes this triad is a normal force. Right? The friction forces are always perpendicular to the direction of the normal forces. So ET and E phi are perpendicular to each other. I define their cross product as E suffix n, pointing into the curvature, positive direction of curvature. So this is your Frenet-Serre triad. It just does not look like one. We would have typically called it as ET, En, and E suffix b. So this is actually the E suffix b direction, the binormal direction. The normal direction and the tangential direction are defined this way. And to top it off, here is what I also want to do. Drop a perpendicular here. Okay, this is the ER direction. And you can clearly see that the ER direction is not the same as the EN direction. Does this make sense to everyone? Is my figure making sense? Do you want any clarifications? Okay, once again I am calling the direction along the slant length of the cone as E suffix t. The particle will be spinning along the surface of the cone. That is your tangential direction E suffix phi, which is the same as this guy. They are the same. E suffix t is clearly not aligned with E3, which means that the cross product of Et and E phi cannot be the same as ER. Okay? So which tells me if I draw E3 here along with right, as long as I don't change anything, as long as I don't change the magnitude, I can keep translating my unit vectors. As long as I don't change the directions, I can keep translating them. So I'm just translating E3, and this tells me that this angle here, we had defined it as alpha. So that angle there is also alpha. Okay? And I'm going to draw these, just these unit vectors, and there's a couple of statements on them. Okay. So Et, E phi, En are a triad. Okay. En is not the same as Er. Et is not the same as E3, of course, as you can see. Which means that if I am trying to break the components of the unit vectors ER and E3, they will have components along ET and EN, but they will not have any components along E phi. E phi is perpendicular to both these sets of unit vectors. So if I write the next one is ER, E phi, E3, the common culprit in this system is E phi, which means that if I am converting one set of unit vectors to the other set by coordinate transformations, ER will have a component along ET and EN, E3 will have a component along ET and EN, or vice versa. ET will have a component along ER and E3, and EN will have a component along ER and E3, whichever way you want to split it. Okay? So that's something to keep in mind. And so I'm going to draw just these two. So I'm not interested in this guy. We already have commonality there. So I have ET. This is EN. Just extending it onto the other side. Here is E3 and ER. This is the same straight line. And I have the angle alpha here, which means that this angle here is also alpha by geometry. And if I need to coordinate transform from one set to the other, we can easily do. And with all this, now I will write the force vector. The force vector will have components in several directions. We need to see what type of transformations we want to perform. Any questions so far, please? Everybody good with the figures? Okay. As you can see, these problems will start getting more and more complicated as you start having more and more coordinate systems. which is the case for three-dimensional problems, rigid bodies especially. So I write the force vector, it's minus mg E3. Maybe I'll write it in now. That will be here, up here, start up there. So force vector F. This is the net force acting on the particle. Okay, so this is going to be minus mg in the E3 direction. Then I'm going to have the spring force. Because of the fact that I'm choosing ET to be positive away from the particle along the slant length, Fs is going to be negative. Minus F spring ET. Then I'm going to have the friction force along ET plus Fc along ET. Then I'm going to have the other friction force along E phi. Then my normal force along EM. Plus N. These are my forces. My mass times acceleration terms. M-A-R-E-R. M-A phi E phi. M-A3. This is A-R. Our degrees of freedom from last lecture were R and phi. We had chosen them to be R and phi. Degrees of freedom. R and phi. So force, mass times acceleration. The force is equal to mass times acceleration, which is Newton's law. With your permission, can I get rid of this panel? Alright, so I just write F is equal to ma. This is very common stuff. Right? F is equal to ma. So write down all the forces on one side, all the acceleration mass times on the other side. Minus mg E3 plus ffg Et. Fs Et, Ff phi E phi, Men, MARER, E phi. And we are now only getting started with the entire problem, in some sense. Okay, after all this work has been done. So my question to you now is, obviously you see that I can't just pluck terms from here and then equate them to the mass times acceleration because this is a mixed system, right? I have unit vectors of all kinds sitting here. So I either have to perform a coordinate transformation from this system to that system or that to this one. Which one would be the better one to do? Should I coordinate transform ET and EN to ER and E3, or should I do the vice versa case? And can you give me a reason as to why, which one is preferable? Yes?
Probably the ET and EN to ER and E3, since your mass times acceleration terms are already in that frame.
That could be one reason. But remember, when you're writing your equation of motion, what should not be there in there?
Constraints.
The constraints should not be there. And in this force expression, the only constraint is this normal force. So perhaps if I perform the transformations from ER and E3 to ET and EN, then all the EN terms will give me the constraint force, and then the rest of the terms will give me my equations of motion. If I had done the other way around, then I would have had components of the normal force in ER and E phi, ER and E3, and I would have to separate them out and then write out many more things to get the equation of motion. So To get the equation of motion, always find out where the constraint force lies and make the coordinate transformations such that you get mass times acceleration in that particular direction. That will be good to go for you. Okay, so that's the reason why we're doing the coordinate transformation this way. I'm going to write it out quickly. E3 in terms of ET and EN. Cos alpha ET and sin alpha EN. Everybody good with coordinate transformations? All I'm doing is taking projections and writing it on there. Then ER is going to be minus cosine alpha En sin alpha E. Spring force, need to write out what that is. So particle is here. This is R. This was Z for us. We need for the spring force this stretched length L. L is a stretched length, which is the distance of the particle P from the point O. This angle is alpha. So L can be written in terms of R and alpha. So this is R, or this is Z, and this is R, perpendicular here. Okay. So I can say that R divided by L is cosine alpha, sine alpha. Means that L is R times cosecant inverse of inverse of sine. Okay, this is a right angle triangle. L is the stretched length of the spring. And so the spring force is K times the stretched minus the unstretched length. So F spring is K times L minus L naught. L naught is some number that is known to us at the beginning of the problem. So I just need to substitute. F is K times R cosecant alpha minus L. I'm going to do a couple of things which may not be necessarily in linear order. Because I have my acceleration expression here, I'm just going to substitute for ER and E3 using these transformation equations. Is that okay with everybody? We're going to continue down here. Okay, so this is M times AR times ER, which is minus M times AR times cosine alpha En plus M times AR sin alpha Et M times A phi E phi M A3 cosine alpha Et M A3 sin alpha En. So I substituted for ER and E3 in terms of ET and En. So that I can siphon out all the En terms, equate them on both sides. That gives me my constraint equation. The rest of it is going to give me my equation of motion. Are all of you following the thought process? Yes.
Real quick, why was the normal force the constraint force?
or the normal force is the force that prevents the particle from doing what it wants to.
Right, okay.
So if the normal force were not there, this would just be a springy pendulum. Right. So constraint meaning it restricts the freedom of the particle. Okay. So now I'm going to collect all the normal forces and write them on here and the rest of the terms. Alright, so the normal terms, En terms, on both sides of the equation. So I'm going to have N on the left hand side. On the right hand side, I'm going to have MAR cosine alpha negative. That's one term in the normal direction. Then I have MA3 sine alpha. So this is my constraint equation. Then my equations of motion, we still need to work out what these friction forces are, right? Because we don't know what they are. So we have to see how to get them. That's the big battle here. Then ET direction, I'm going to have the following. I have mg times E3, which I also need to resolve into components. Sorry, I forgot one thing here. It's not just the normal force in the En direction. This is minus mg cosine alpha Et sine alpha En. Apologies, I need to add in an extra term here. I'm going to bring it on to this side. It's a minus mg times sine alpha becomes a plus mg sine. Okay, what did I do is that I took this E3, which also has to be resolved into ET and En. Its component along the normal direction is minus mg sine alpha, which should have been written here on the left hand side. I brought it over to the right hand side. The negative sign vanishes. So this is the normal expression, normal force expression. Then we do something similar in the ET direction, so the friction force Ft, that's first one. Watch this. All of the forces that have the ET, except for the friction force, I'm going to bring it onto the right hand side. Okay, so that I just isolate this friction force Fft and Fff on the other side. So this is going to be first of all MAR sine alpha in the ET direction. There's one there. Then MA3 cosine alpha in the ET direction. Then I'm going to have minus mg cosine alpha, bring it onto the right hand side, so plus mg cosine alpha. Minus fs on the left hand side, bring it to the right hand side. Plus. This is the friction force. Same thing in the E phi direction. Isolate everything besides the friction force. F phi, I'm sorry, is going to be fairly simple. MA phi times E phi. I have no E phi here. This time. All right. Any questions so far?
No, I don't.
So you're not seeing the equation of motion yet. The equation of motion will happen once we start substituting for the acceleration terms. But what about these guys? You know, who knows what they are? We don't know them yet. Right? So we need to figure out a way of actually finding what the friction forces are in terms of the degrees of freedom of the problem, and only then you can actually solve this kind of a problem. Okay? So now I'm running out of space. So I'm going to keep this panel on all the time and this on all the time, and I'll work with only these two. Okay? Let us first look at the static case. When I mean static, the cone is still rotating. I'm not saying that is not happening. The cone still rotates at a rate of omega and omega dot and so on, but the particle is stuck to the cone. The particle does not have any freedom to move. If the particle is stuck to the cone, what is r dot and what is r double dot? They all have to end up being 0. Phi dot, phi double dot will end up being 0. Okay? So this implies that r dot is 0, r double dot is 0, r becomes just some value r naught, which is some L naught times sine alpha. If you remember, the unstretched length was L naught, so if the particle is statically at the unstretched length, it is just going to be a part of the cone, it will just be spinning along the cone. It will not be moving relative to the cone. Okay? And then phi is some angle phi naught, I don't know what it is, it doesn't matter really. Some constant value. Okay, so these are both constants. You can just leave them as r naught and phi naught if you would like. And phi dot is 0, and phi double dot is also 0. Omega is not 0, omega dot is not 0 because the cone is still rotating. I'm not saying the cone is stuck. Then that becomes a really silly problem in basic statics. We want to do something a little more than basic statics. Okay, so cone rotates, so I have omega and omega dot. These terms are still there. Let me take a look at my normal force in the static situation. The normal force in the static situation minus m cosine alpha AR is this term, but R double dot is 0, phi dot is 0, so I'm just going to have minus R times omega square, and so minus becomes a plus. This is R naught omega square. Is everybody comfortable with what I'm doing here? Okay, I'm taking the static case. I'm looking at my acceleration components. In the static situation, everywhere I have an R double dot or a phi dot or a phi double dot or an R dot, all of those terms are gone. Okay, so this is gone. This term is gone, but the omega is still there, so that's minus R omega square. Pick up another negative sign there from the normal force. Same thing, plus mg m sine alpha times A3, which is here, R double dot is 0, so I don't have anything from there. So I don't even need to include it. And then I'm going to have mg sine alpha. Static case. I have to do the same thing for the friction forces. Okay, so Ft static, and you'll see why we are doing this in a minute. M times sine alpha times AR, that's M times sine alpha. AR in the static situation is just going to be minus R omega square, so this is minus M omega square R then I'm going to have ma3 cosine alpha. A3 is 0 in the static situation because r double dot is 0 in the static situation. Okay? And maybe I can list those things down here. So AR is just minus R omega naught, R naught omega naught omega square. A3 is 0. A5, this is all in the static situation. R dot is gone. Phi double dot is gone. And so I'm just going to have R omega dot. This is in a static situation. And so I have to include that. Mg cosine alpha. There is no spring force when I'm in the static position, and if I'm assuming I'm at the unstretched position statically. Okay, so Fs is also 0 for me. Same thing for F phi in a static situation. That's m times A phi, so that's m of omega. And so when we start simulating these problems, this is what you have to do. Given omega and omega dot, given an R naught and the P naught value, essentially, you have to check and see if the particle is actually in motion relative to the cone or not, to begin with the problem. And how do you check that? Is by checking the friction forces and seeing if they are breaking over the impending motion conditions. Okay? So for impending motion, or for static situation, the net friction force, Ff, is less than or equal to mu k times the magnitude on both sides. So this is a static situation. Net friction force is nothing but the square root of the sum of the squares of its components. And so, Ft static and phi square yes.
Wouldn't that be mu s?
Oh yes, mu, yes, I'm sorry. No. So after all of this stuff has been done, after you obtain some general equations, what you have to do is this. Okay, is the bead actually moving relative to the cone? If it is not, then this is just something moving in a silly manner, right? It is just moving, rotating along with the cone. Its motion is already known to me, because the motion of the cone is already known to me. How do I check that and see? Is by first calculating this guy, which can be done because I have all the parameters here. Calculate this guy, which is R naught, I'm sorry. All the parameters are known. Square root of the sum of the squares. The coefficient of static friction will be given to us. So that's also something that will be given to us. Coefficient of kinetic friction will be given to us. Check and see for impending motion. If this inequality is satisfied, you don't have a problem. You're done. You don't need to do anything more. If the inequality is broken, that's when life becomes more miserable. We have to go through some more stuff. So this is the first step in every problem that you'll be doing when you're performing the simulations. Select a set of values of all these quantities such that this constraint is broken, so that you have actual kinetic motion taking place. Okay? So that's a big field of dynamics in some sense, parameter evaluation. For what values of parameters or what ranges of parameters do I actually have motion? Any questions so far before we go to the next more messier situation? Everybody good to go on this? I'm going to take this panel off. Okay? So this is always your first step in every problem. Check and see if there is motion taking place. If there is, then we do the following. So if the inequality is broken, so motion what we have for motion is that we have an equation f magnitude is mu k times the magnitude of f. Okay, so this is one equation that we do have. And let's write down all the things when motion starts taking place. Normal force, now we don't have phi dot 0, we don't have r dot 0, we have to include all of those features. That's minus m cosine alpha times all of these things. Minus m ar cosine alpha. None of them cancel off. ma3 sine alpha. And md sine alpha. Given AR, given all of these A3 terms, you can calculate the magnitude of the normal force. Okay, so you can obtain the magnitude. But this equation is not worth it for us because it does not tell me how to actually find out f suffix t and f phi. How do I even know what ff is? Just take the square root of the sum of the squares, but that's not going to be sufficient for me. So here is what we need to do. For motion, we write the stronger statement. The stronger statement is vector f, the friction force vector, is minus mu k, magnitude of the normal force, and then the relative velocity between the bead and the cone divided by magnitude of the relative. This is the stronger condition, right? The stronger equation or the vector equation for kinetic motion, kinetic friction. This term essentially tells me the direction of the velocity vector. Right? I take a vector divided by its magnitude, tells me its direction. And the negative sign tells me that the net force of friction is always opposite to the direction of the relative velocity vector. Okay? So the big question is, what is the relative? The relative is the following. It is the velocity of the bead as it is with respect to an inertial observer. So this is v p suffix o, which we have calculated here, minus velocity of the bead if it is stuck to the cone. Does this make sense to you? Velocity of the bead relative to the cone. This is the relative velocity. Velocity of the bead related to the cone is the total velocity of the bead with respect to an inertial observer minus the velocity of the bead as if it were stuck to the cone. P slash O is known to me. If the bead were stuck to the cone, what would the velocity be? Can somebody help me out? Just by looking at this, if the bead were stuck to the cone, if there was no relative motion between the bead and the cone, what would the velocity of the bead be? It would just be r times omega. Right? Because all the r dot terms will cancel off. There's no relative motion. Okay? this guy, if I write it out, so we feed stuck to the cone is just R omega. It is just sitting there and spinning along with the cone. Its velocity is going to be whatever radius it is sitting at in the tangential direction. And please stop me if I am not clarifying anything clearly. We use this problem as a template for solving every other problem that we are going to be doing from now on. So I don't want to go through all of these steps again for each and every problem. Okay, we will make use of this and say, okay, we've done this once, just follow the same path. Okay. Any questions on this one here? All of us good to go? Yes.
So this is valid for all points in time, like the velocity that it would be if you were stuck on the cone, because R is.
Absolutely, absolutely. Whatever the R is at that instant in time.
Yeah.
So you see, I did not write this as R naught.
Right.
Okay. So then I calculate this guy. This is fairly easy to calculate. Okay, I'm just subtracting this R omega from that, and so I end up with the following. If you do the subtraction, it's R dot ER plus R dot by tan alpha E3, and then R phi dot theta. So this is the vector V relative. Its magnitude is the square of the sum of its components and square root of that. Is R dot square and alpha square dot square by dot square to the power 1 by 2. And I'm going to assume that we know how to find this if we know the variables of the problem. We don't know yet, we haven't solved anything, so I'm just going to keep it as it is. So I'm going to keep this as it is, I'm going to keep this as it is, and I'm going to equate this and that. Okay, so I'm going to go back to my friction equation. Right? So we have vector F is the following. F in the tangential direction, F phi in the azimuthal direction, the phi direction. This is equal to minus mu k magnitude of n, magnitude of V relative. All of these are magnitudes, so just write them as a big lump, and then V relative. The vector V relative. So we have an expression for this, we have an expression for this, and now I'm going to equate the vector terms on both sides, and you'll see how much fun this is. Can I get rid of this one? I'm going to get rid of this one here. Alright. So what am I planning to do? What we want is that we don't want, if you really look at this panel, focus on this panel here. This is okay, the normal force equation. You can't do much about it because if you want to calculate the normal force, you would have had to calculate the acceleration terms, which would only be obtained if you solve the problem. We haven't done that yet. So I say, okay, hey, this is the constraint equation, which means these two have to be the equations of motion. I have 2 degrees of freedom, so I'm expecting 2 equations of motion. But the big problem is, what is this guy? And what is this person here? I have to write those two in terms of the problem parameters. That is r dot, phi double dot, r double dot, or whatever it is, combinations of that. And how do I get that? Is by making use of this equation here, this vector equation here. Okay? So if I express this out, look at this. So ft dt fy e phi, this is equal to, I'm going to call this as some, let's call it as some magnitude, capital M. Okay, so this is a minus M times, I want to convert the relative velocity terms which are in the ER and the E phi and the E3 frame to the ET and the EN frame, so that I can just siphon out FFT and FF1. Okay? So if I do that, this is R dot multiplied by ER transformation equations. We wrote this some time back. It's going to be minus cosine alpha En sin alpha Et plus R phi dot E phi plus R dot tan alpha. E3 was cosine alpha Et sin alpha Et. So in reality, I had 4 unknowns to begin with at the problem. I don't know the 2 degrees of freedom, r dot and phi dot, r and phi, I have to calculate it, so that's 2 unknowns. The normal force is the 3rd unknown, we don't know what it is. And the friction forces, which combined together written as a vector F, is also an unknown, so I have 4 unknowns. What are my 4 equations? Well, actually 5 unknowns, right, because 2 components of friction, so 5 unknowns. I need 5 equations, I have 3 equations right here. I need 2 more equations, which is going to come from the friction normal force relationship if I equate the ET terms on both sides. If I equate the E phi terms on both sides, I will be able to write FFT and FFI in terms of the degrees of freedom. Then I take those guys, throw them into the blender here, use MATLAB to solve it, and get an idea of how the motion takes place. Okay, so, and you'll be thinking, okay, hey, what about this normal term guy? Does that cancel off? And I hope it does, because then we have made a mistake somewhere. Okay, so I take the ET terms on both sides. FFT on the left hand side. On the right hand side, I'm going to have minus r dot sin alpha. Okay, minus m. Sorry, minus m times r dot sin alpha, and then cosine alpha divided by tan alpha. I think there is a mistake somewhere. This should be flipped, I believe, or one of them should be flipped. No, here. So I'm going to have this term here, and then r dot cosine alpha by tan alpha. And that's it. That's FT. Then E phi direction. What are the terms? FF phi minus m once again, which is that magnitude term that we just wrote. And then I'm going to have r phi dot E phi. And that's about it. Okay. And then the last one in the EN direction. balance once again. 0. And then I have the following terms here. Minus r dot cosine alpha. This is the hour that we are waiting for, right? These terms, if it is 0 here, this should also end up being 0 here. If that does not happen, then there is some mistake somewhere. So hopefully this is r dot divided by tan alpha times sin alpha. So plus r dot by, sorry, tan alpha is sine by cosine. So this is sin alpha by cosine alpha times sin alpha. So everything lines up. This is cancelled off with that. The cosine alpha comes to the numerator and everything becomes 0. So this entire term is completely useless information. But we are vindicated in some sense. Capital M here for us is minus mu k, normal force, V relative. And so I will write the final equations of them. First one. I'll write the easier one first. This guy. Okay? F phi is now going to be minus capital M R phi dot. I should not be writing the unit vector here, I'm sorry. This is just R phi dot. If I write the unit vector, I should write it on both sides. This is cancel off anyways. This is equal to little m times A phi, which is that big guy there. So A phi is Coriolis 2 r dot